All right, for the take-home circuit test, we're going to go ahead and crank through the free response problem that I gave you. So I think this one's an old one from like 1985. But anyway, here we go. We've got this circuit, and you'll notice that there is a battery, and hooked up to it in series, there's a resistor, there's a switch, and then it's going to branch and has a choice of going through a second resistor to get back to the battery or going through a capacitor. This circuit happens to be just like the circuit in the packet, right? Yeah. In your unit packet, there was a sample circuit that I set up as a demo in class, right? This is the same as this circuit. Okay, I've got a battery. I've got some ammeters and voltmeters thrown in, but I've got a battery. It's going to go through one resistor, and then it has a choice of going through a capacitor or a second resistor to get back to the battery. Because the battery goes through a resistor, then has a choice going through a capacitor or resistor to get back to the battery. Same setup that we did actually in class. Didn't do it purposely that way, just noticed that it was the same circuit when I was working the problem earlier. So here we go, let's work this real quick. So here we go. In this circuit, I1 and I2 are the currents going through resistor 1 and resistor 2 respectively. V1, V2, and VC are the potential differences across these. Yeah, it bugs me always that they use V's instead of delta V's, but yeah, trying to buck a century of convention here. Anyway, point is, those are the potential differences across resistor 1, across resistor 2, and the delta V from one side to the other capacitor. Calculate the current immediately after the switch is closed. When I first close the switch, you say, hey, this thing's uncharged to start with, right? And so when I first hook it up here, close this, I'm hooking it up to voltage, and so current, this is not going to stop the flow at all. The flow to the plates will come, unhindered. In the first instant, just acts like a bare wire. Hey, a bare wire from here to here, that would short circuit this resistor. So in the first instant, this resistor isn't doing anything. It's just like I have a circuit like this, and this is acting like a bare wire. So it's like I got a circuit with just this resistor. So that current here at the start coming out, if I did my delta V is IR, then you'd say, yeah, that current coming out, my voltage is 3,000 volts. It's going to be that I1, right? And then it's the only resistance is this. So 5 times 10 to the 5th. And so you're like, okay, well, what's 3,000? That's 3 times 10 to the 3rd divided by 5 times 10 to the 5th. 3/5 is 0.6. This is going to be times 10 to the minus 2. So that'll be 0.006 amps is my current. Okay, B. On the axis below, sketch the potential difference V2 as a function of time. So that's the voltage across this guy. In the first instant, there is no charge on the capacitor plates. So the voltage in here, remember all this is at 1V level, right? And the delta between here and here has got to be 0. It's not charged yet, right? So this is all 1 voltage here. So at first, the delta V from here to here, there's no delta V across this, so it's 0 is the delta V across that guy at time 0. So this graph is going to start at 0 volts at time 0, the delta V from here to here. I'm dumping all my voltage off at this resistor and like all the currents going around this way in the first instant. Okay, but as time goes on and this starts to charge, then I'm going to start getting some current flowing through this guy, and there'll be a delta V there. Well, wait, all of this is at 1V, all of this is at 1V, it's just the delta V of the capacitor is the same as the delta V of this, right? And so as this charges up, the voltage across this gets bigger, and the voltage across this guy it's the same delta V, right? And so it's going to get bigger and bigger. This is going to be one of these, where it's approaching a final value. Do we know what that final value is? Well, sure. Eventually, at the end, this will act like a break in the circuit, right? It'll be fully charged and no more charge flows to the plates. And so the delta V for the capacitor is going to be the same as the delta V here for this guy. And at the end, basically, no more current flows through here. It's just current flowing around in this loop, right? And so I've got the 3000 volts, and I'm going to go down IR here and down IR here. So I might just notice right away this is 5 times 10 to the fifth, and this is 10 times 10 to the fifth. It's like a 1 to 2 ratio, right? And since delta V is I times R, and it's the same current in both these guys at the end, it just flows around at the end. So then I'm going to go down I times, 5 times 10 to the fifth, minus I times 10 to the, this is going to be double the voltage drop as this one, because it's double the resistance. So it's a 1 to 2 ratio. It's 3000 volts, so it'll be 1000 to 2000. The delta V here will be 2000 at the end. So 2000 volts is the value there that it's approaching. Did I need to do that to get the points? Sometimes they'll say things in a question and they'll say, like, indicate any important values, or significant values. And so they'll want you to calculate, like, set values like that you can. They didn't specifically ask you to do that here. So, that's the sort of thing I might go back and do later and fill in if I need to. But if I have the inclination, but I don't think that you needed to do it to get the points on this one. Okay, here we go. Now it says, assume switch S has been closed for a long time. And you see how this is like, I should have put some more space in here, but this is like a heading. So like everything that comes after it, right? So this is a header and these are indented. All this is, well, sort of indented, assumes this applies to everything after it. So now the switch has been closed for a long time. And so what's the current I2? Well, you know what? This value I just figured out, I could just use that now if I wanted to. But we'll just do it the way that, assuming we hadn't done that. The current's just flowing around like this at the end because this acts like a break in the circuit. So I'm going up 3000 volts. I got to go down 3000 volts going through those two. If I do my delta V is IR, I'm going down 3000 volts, and that'll be my current, right? I1 and I2 are going to be the same, right? The current's just flowing around here. So it's just that I times that resistance. The total resistance here is 5 times 10 to the fifth plus 10 times 10 to the fifth because they're in series, one and then the next. So that's 15 times 10 to the fifth. So if I rearrange this, 3000, let's see, like 30 divided by 15 would be 2. So this is like 200 divided by 10 to the fifth. So that's just 200 move it 5 decimal places. So that'll be 0.002, right? 1, 2, 3, 4, 5. Yeah, 0.002 amps. That's the current in that after a long time. Okay, D, what's the charge on the capacitor then? Well, the delta V for the capacitor is the same as the delta V here, so that I'm going to use that 2000 volts I figured out before and say, well, I could just, I didn't make explicit how I got it though. I need to show my work. So I'm actually going to go back and say, you know what, we just found this current that's flowing through here. Isn't it true that the delta V for the capacitor is going to be the same as the delta V here? And the delta V here I can solve. Now that I know the current through this guy, I can say delta V is IR for this guy. So the delta V here to here, which is the same as this, delta V here is going to be I times R. So my delta V for resistor 2 is going to be that I2 times R, and that I flowing around here we figured out was 0.002, and the resistor for that guy is 10 times 10 to the fifth. There. 2 times 10 would be 20, but this times a 1/1000th. Would be 0.02, but then times 10 to the fifth. So I'm going to get that that's 2000 volts, which is what we figured before. Now I know that's the delta V from here to here. The same as the delta V from here to here. Well, the reason why I did that is because I know that capacitance is my charge per delta V. And the delta V for this is the same as here, right? Because all this is one V value and all this is another V value. So C times delta V is my Q. So the capacitance they told me was 5 microfarads, that mu, that's times 10 to the minus 6 farads, times the voltage I just figured out was 2000. That's my charge. And so, you know what 5 times 2000 would be? Yeah, that'd be 10,000. but then I got to do times 10 to the minus 6. So 1, 2, 3, 4, 5, 6. So 0.01 coulombs would be my charge on that capacitor. Okay, so that's part D. There's a backside. Part E, calculate the energy stored in the capacitor. Oh, well, I've got a formula for that. The energy stored in a capacitor, that's going to be 1/2 capacitance times the voltage across the capacitance squared, right? 1/2 CV squared. And so you say, okay, well, the capacitance, that's 5 times 10 to the -6, right? It was 5 microfarads, right? Yes. And the voltage across it, we figured out multiple times now, was 2000 volts. So let's see. This is like a 2 times a 2 times 1,000 times 1,000, right? So 2 times 2 to 10 to the 6. Okay, one of these 2's is going to cancel with that half, you know what I mean? And the other 2 times that 5 will make a 10. So I'm going to have a 10 times 10 to the -6 times 10 to the +6. Oh, it's just 10 joules is my energy in the capacitor. And lastly, part F, we're going to open the switch. So we first closed it, we charged this up all the way, now we're going to open the switch. When I open the switch, I'm taking this stuff out of the circuit, right? So I just have this. So I have my charged capacitor that now is going to discharge back. It's going to push charge back around, right? Charge can run through here to get to the other side. So my hypothetical current would go this way. So that's what's going to happen. So I have that charged capacitor and current flowing through just R2. They want to know the current is a function of time, current through resistor is a function of time. They say, well, and note, oh, look, they say clearly indicate initial and final values. See, this is when they want you to put those numbers on the graph. Like I said, I got that little circuit there, waka waka waka, right? This started off being 2,000 volts, right? And this is that 10 times 10 to the 5th ohms, right? So they want the current. So I'm going to start off with a big current. As this thing starts off fully charged, I'm going to push big current over time as this discharges. There's a smaller and smaller E field in this as there's less and less charge on the plate. So smaller E field pushing charges around in it, so the current goes down, 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 down. This is going to be one of these asymptotic approaching zero current versus time graphs. Important values. The only really important value to know is that starting I value, right? What's the starting current? Well, in this circuit, if I start at the first instant, it's 2,000 volts across the capacitor, and the resistance is this. I can do a delta V as IR at that first instant, that starting current. So 2,000, I'm going to go up 2,000, I got to go down 2,000 through the resistor. That's going to be that initial current times the resistance, 10 times 10 to the 5th. Well, we could just call that 10 to the 6th. So 2,000 divided by 10 to the 6th, that's like 2,000 times 10 to the -6. Move 6 decimal places, 1, 2, 3, 1, 2, 3. So it'll be 0.002 amps. So that's this value here. If this is my I in amps and time in seconds, whatever. This will be 0.002 amps. There's no other values, because like this doesn't hit the axis. It doesn't hit till infinity. So there's no values I need to mark, no intersections there. There's nothing else special here. I mean, I guess we could calculate the time constant and indicate where that happens. They don't want that. This is all you need. I'm fairly confident. So that's the free response. Yeah, that's the free response. Parts A through F. Nowadays, they have gotten to the point now where they take problems and they chop them up into more smaller chunks typically, and so you get problems now that have multiple subparts on each. And but this is a nice little RC circuit problem. Yeah, it's a good one. Good review.